Is the mic on? I think so. This is what I have an outline to talk about. I'm very pleased for this to be interactive. I have plenty of questions for the audience here, but if you want to ask questions at other times, just go ahead. I believe we're paying you, so that's okay. Interesting. That's one of your minutes gone. Okay. So you probably have heard a little bit of the history in Marcus's talk and through out-of-band connections. What we have done essentially is to accelerate support for virtualization support in this machine monitor thing that we're building. This was made feasible by the acquisition of the VPC team. The other thing that's happened probably since we last talked to you is that we were building a high assurance operating system as one of the guests of our isolation kernel, and we talked to you a year ago. And that's been replaced by Windows variants, and I will be talking about some of the challenges associated with that too. So what are we trying to do? So there's a huge security space we can think about exploring, given a virtual machine monitor with security characteristics, plus thinking about having operating systems with different security configurations. The three specific things that we are targeting with highest priority, and again, feedback is very interesting here, is having multiple, think for now, essentially disconnected Windows configurations with different security configurations. So in extreme cases, you could think of a lockdown one managed by your corporate IT department versus one, say, managed by your kid or for surfing the internet. Other slightly more esoteric things like having open configurations which are disposable, that are, say, do not have any persistent state or very much persistent state. So if these things get exploited, they just go away when you reboot the VM. We're also building a specific high assurance guest for writing applications where you are unwilling to take the security guarantees that can be offered by the various Windows security configurations that I'll be talking about. The essential challenges that arise going from where we were a year ago to where we are now is, you saw in Marcus's talk that we have the specific hypervisor architecture which is being built has a rather ill-defined TCB, trusted computing base, and in order to craft up some interesting security environment in this world is challenging to us. The other thing I'll talk about is the sorts of things you can do in Windows to configure it better. Okay, so this part of the talk is about the specific hypervisor architecture which Marcus described has some interesting and challenging security characteristics. A little bit more detail about what they are. I understand from feedback I was getting this morning and from hearing Marcus talk that this has already come up a bit, so if I'm being repetitious, you can move me on. So the hypervisor has a fairly well-defined security role. It manages some very specific devices like memory, the CPU, DMA protection. It provides some rather well-defined security software objects, if you like inter-process communication and, I don't know, semaphores, whatever it turns out to be. And this is all fine. If you're running on top of the hypervisor, you can think when you're looking down using these services that the hypervisor represents the trusted computing base, and if you call a hypervisor function, that it's going to do exactly what you expect it to do. The security challenge is that most of the devices are in the system are exported to guests. And furthermore, most devices in V1 of the system are exported to this thing we call the primary guest. So the challenge becomes in defining and thinking about exactly what your trusted computing base is. So, a simple example is if I need to talk to the network, I have to ask one of my peers, another virtual machine, who might own the network card, to forward a packet for me or receive a packet for me. Things are even more peculiar than that, because the disk itself is owned by a guest. Traditionally, when high assurance hypervisors were built, you had a much more well-defined TCB. You had a disk owned by the hypervisor. You had a teletype owned by the hypervisor, and you could use these. You could trust the virtual machine you're running on. Now, you have to ask yourself the question, if you're talking to peers to get work done, exactly what is the trusted computing base? And naively, if in order to run you're using the disk and the network and whatever else input and output hosted by the primary guest, it's probably not too far off to say that your trusted computing base is all of Windows, and that's probably going to be 120 million lines of code by the time we get to Longhorn. So that's bad. The next thing that's bad is the primary guest is going to be where performance is snappy, where you have accelerated graphics, where you have direct access to the disk and the network. So users are going to be inclined to run most applications there, and this means that the primary guest, the thing that owns all the devices, is essentially going to be the most adversarial environment on the machine. Lots of random third-party programs, lots of device drivers of questionable quality. So the challenge, which I'm talking about in the first third of the talk here, is trying to recognize what these problems are and talk about the remediations and mitigations that we're thinking of doing. So what are the problems? What are the possible solutions that we could do? So one thing we could do is to say, no, you can't run random applications in the primary. We're going to lock it down. We're going to say that this is part of a well-controlled trusted computing base, and we will, by fiat or by policy encouragement or whatever, say that applications are going to run in more controlled environments, like non-primary guests or just guests. This would be fine. The problem with that is you lose the performance benefits of the primary, and from a security perspective, it's largely going to become very similar to a hosted virtual machine monitor, right? It's you're not getting much security benefit from having a hypervisor here. Next thing we could do, and I believe this came up also this morning, is to move drivers into the hypervisor. This has two consequences. One thing is you have to support an open driver model in the hypervisor. It's probably a little bit worse than that. You probably have to provide backwards compatibility with existing device drivers that are out there. So what you're essentially going to be doing there is building a hypervisor which is based on NTOS kernel, because you can't tell people to go and write device drivers from scratch. So this also to my mind at least turns into a hosted VMM model as well, at least from a security perspective. The vision, and this is something we would like feedback on, is to, as we go forward, move, better define the trusted computing base by putting important devices and services in a place that's away from the primary, and putting, or let's say, getting away with the idea of the primary. Having some sort of ad hoc assignment of devices to guests, and putting those resources that you want to have high security or high availability in a place where a crash in some other part of the system won't affect that set of services. Have you covered this already? I mean, this seems to me one of the big questions that we're looking for feedback on. Does this make sense? No.
Yeah.
We believe that's good.
Do you want to say what the opposition to this idea is? Because we haven't heard it.
So I think the opposition is, I'm not opposing, I'm genuinely seeking feedback. This is the direction that everyone thinks is the right thing to do. I guess I have personally not thought deeply about whether a 5 to 10 year investment in getting this right versus a 5 to 10 year investment in fixing up Windows, what at the end of it would provide the right balance of security, performance, usability, availability.
And it's 5 to 10 years because of the hardware change? Or just
I guess I've been working at Microsoft long enough to be very conservative about my estimates of how long it takes to even make a small change in Windows. Making some sort of a profound architectural shift where we don't know what the hell's going to break. I have a few words later on about the sort of componentization efforts we're doing. We're trying to make Windows more compartmentalized and trying to remove all the interdependencies within it. It's a massive undertaking.
independent of the hardware, it's going to take 5 to 10 years.
Yes. Yes. You have 60 million, you have 120 million lines of code. You have to support essentially all devices created since the beginning of time and all applications created since the beginning of time. You can't ship an OS release which is slower than the last one that went out unless the world changes. So these business constraints make it very difficult to innovate in the OS space, in my experience.
It strikes me that, given that the early versions of Windows were not written with trustworthiness very much in mind, and you're more conscious of it now, and as time goes on, you're getting better and better at writing that code. In a world where you own all the software interfaces, which is to say you don't have compatibility problem, you're always better off if you can figure out a way to write a new one. So the argument that you're going to spend 5 years writing new things versus spending 5 years trying to update an existing Windows-based code base, you're better off starting again because you'll be much better at it, it will be smaller, and you don't have a reverse compatibility problem because these interfaces are interfaces that only you will deal with anyway.
Right.
So my understanding is that third-party drivers, I think from a reliability point of view, the third-party drivers are a serious issue. To the degree that they can be isolated, it seems very good. So I can't help but think you're going to be forcing on that task.
Yeah, and this is exactly the thinking that we are doing. The problem doesn't go away. If a third-party driver crashes, the kernel has certain expectations and state and stuff, and being able for the rest of the system to recover is non-trivial. But yeah. So anyway, that is the vision. The final thing, at least on this slide, that we could do is to use crypto. And the analogy here is when you talk on the network, you're also using the outside world, and you don't really trust the outside world. And if you wrap some crypto around data you exchange with peers or let out of your address space or admit into your address space, into your OS address space. If you wrap crypto around it, you have certain guarantees or certain protections that you wouldn't have otherwise. And I'll talk a little bit about that. So the challenge with doing crypto is where do you put the keys? The system we've been describing up until now, a guest boots out of the disk. The disk sits sits within the primary. So if you want to have a communication that you believe cannot be subverted or observed by outsiders, you need to craft up a key from somewhere, and you need to maybe store a key. And how do you do that? One of the pieces of hardware that we have to help us with that is this device called the TPM. It's a little crypto processor. It's designed by a committee. Shows it. We were early contributors to that committee and are continuing our involvement. Used to be Intel and some OEMs. It's expanded out, and these are the primary technical contributors now, I would say. We have added to it has been AMD, a bunch of TPM vendors, and a couple of infrastructure guys. And I think Wave Systems and VeriSign are the most active in that space. I'm not going to talk about the TPM very much because it's fairly well understood and fairly public right now. The bit that's interesting from our perspective is, I guess, these three top bullets. It provides a way of authenticating software booting on the platform. So this weird problem we have where the hypervisor itself is kind of loaded off the disk, which is owned by an adversary. The TPM provides a way of saying it doesn't matter how the hypervisor got into memory. The hardware will, in some sense, authenticate the hypervisor and will provide crypto services gated on that hypervisor identity. Provides key storage and implements some crypto algorithms, half a dozen other interesting features. So in a little bit more detail as to why the TPM helps us out with this where to store your keys bind, the sort of at a very high level, when a hypervisor is spun up on one of these new platforms, the hardware does this little dance where it effectively measures the hypervisor that's running and stores the identity, in concrete terms, the hash of the hypervisor, away in some internal register somewhere. Doesn't matter if how the hypervisor got into memory. This function will work. The important thing to appreciate here is that if the primary was corrupted and the hypervisor was changed or whatever happens, then the security characteristics of the hypervisor you want to run versus the hypervisor you don't want to run are different. So if you have data that you want to remain confidential, or at least within the security perimeter defined by this hypervisor, then the TPM can provide that sort of guarantee. So basically system software gets to store keys. It can, when it's storing a key, it can put a little access control list, if you like, on the data it wants to store, saying precisely who it wants to be able to have access to this data. The practical consequence is guests, operating systems can store data that can either be made inaccessible to other operating systems, inaccessible to other hypervisors, or accessible to specifically authorized system software, hypervisors, or operating systems. You don't take a security dependency on other guests for this service. We will provide TPM access as part of the trusted computing base. And what does this do for you? Well, crypto goes so far. It provides confidentiality. It provides some cryptographic integrity guarantees. It does not provide everything you would want from your trusted computing base. It doesn't provide protection against deletion of data, for instance. If you're sending a packet out on the wire, a bad guy can eat that packet. If you're sending a sector to the hard disk with the plea that it be put somewhere embedded in Rust somewhere, the primary or an adversary can stop you from doing that. Okay, so that's the TPM, and I have about 4 more slides talking about sort of what the security characteristics are of this model we're talking about now, where we have a well-defined, high-assurance, isolation virtualization kernel for certain devices, CPU and memory, and other devices are owned elsewhere. So I just picked two here as sort of illustrative of what the hypervisor gives you. The hypervisor owns memory and maintains access protection over memory. So if you give memory to a guest and the guest decides that it doesn't want to share it with anyone else, the hypervisor will provide a guarantee. The trusted computing base embodied in the hypervisor will provide a guarantee that that security request is met. However, we're still in this sort of denial of service mode that if you want more memory, you have to talk to some other guy to get that memory. The way the V1 architecture is fleshing out, you're probably going to be relying on the charity of peers, the primary guest, in order to get more memory, and you can be starved. This could result in an exploit. It could result in a crash. You have to be sort of careful in your memory allocation to achieve the security characteristics that you want. CPU. So one of the nice things when you're thinking about this from a security perspective is the new processors, for instance, the Legrand processor out of Intel, fixes some of the virtualization problems of x86. So whereas writing a CPU emulator, virtual machine monitor, for x86 was a fairly challenging business for experts, it sort of, in some sense, it's become very easy. So I think we can see quite a few people doing, building various sorts of monitors around these new technologies. Still some issues around the CPU were scheduled by the primary, so the primary can starve the hypervisor. If you're running a multi-threaded operating system, no one's built an operating system so far with the presumption that the hardware is scheduling processors adversarially. We are in a world now where that might be the case. So will the OS stay up or stay secure if some adversary can throw processors at you and stop them at arbitrary places? Don't know. We'll find out. One of the challenges of going from a fairly building an OS with clear specific assumptions on what the guarantees the TCB can provide you versus taking an existing OS and trying to get it to have the security characteristics you want in this environment.
Not to build a simple schedule, but a schedule that makes rigorous guarantees in the hypervisor, just give long-term the illusion that it's running on a somewhat slower machine.
Yes. I don't think I can do it justice because these decisions were sort of made 3 to 4 months ago. But let me say a few words about some of the challenges we have. One of them is the much more aggressive real-time guarantees that Longhorn is going to be providing. So there are some that think that the clock in Longhorn will be running by default at 8 kilohertz. So with 125 microsecond periodicity, the scheduler is going to be built with the assumption that it gets pinged every 125 microseconds and gets to make scheduling decisions. What you would like the hypervisor to do is provide the illusion of a slower processor in order to not confuse schedulers running in guests. The overhead of doing that in terms of what we know about the context switch time and the interrupt handling time for the silicon that's coming out in the Longhorn time frame is the performance tax on the thing is going to be 30% or something like that. So I think that's probably the main reason. I guess the other reason is the it's just a simplicity thing. We already have a fairly sophisticated scheduler that can be leveraged for our purposes. I see going forward, this is just me speaking, that what you would want to do is to move the scheduler into one of these out of the primary and into some other guest. And that it would still be basically the Longhorn scheduler written by Dave Cutler, which would be scheduling the whole system. But again, that's just me.
So you wouldn't see putting a simple scheduler in the hypervisor and letting everybody and publishing what it provides, and then letting Cutler and all the other wizards write their scheduler around the slide.
I would be delighted to have you in the room whilst trying to have that conversation with Dave Cutler. No, I don't know. Both approaches seem to have merit. The performance issues aren't going to go away. We could certainly work around them if we had a hypervisor scheduler and a Longhorn scheduler that was hypervisor scheduler aware. One of the sort of big questions I think that this brings up is, to what extent are we really building a separate hypervisor and a bunch of guests that are largely independent? And to what extent are we building a Windows that has a mechanism underneath it to allow Windows to protect itself? So to what extent are we two things, and to what extent are we one thing? And everybody has a different opinion there.
So let me just be clear. I see this as a performance versus assurance argument. That's really what I'm only pushing to have a simple schedule in the hypervisor because it gives you a way to have assurance and not depend on complicated scheduler for certain parts of the world.
You're right.
That's the trade-off.
Yeah, you're right. And lots of people fought long and hard to get a scheduler, Marcus being one of those people. But have no illusions that this will be an easy thing to do and do glitch-free audio when the AV guys are working with the presumption that they're going to get a DPC every 125 microseconds.
And if they got it every 250 microseconds, they couldn't do anything? Do they know? Do they just pick 125, or is that really as far as they can go?
So I have no idea why 125 microseconds is what they want. I did hear a conversation between Dave Cutler and the AV guys saying, if you want it to be 125 microseconds, you have to show to me that for a sensible scenario, 250 microseconds causes glitches. So people are pushing back on this decision. Our 30% overhead may get down to 15% overhead. Maybe it's acceptable or not. But, yeah.
That's a very simple kind of orthogonal question. Nobody said to me whether a hypervisor will run on a machine which hasn't got TPM in it. Is that true? Or
It is, yes.
it will run
Yes.
on a regular machine?
Yep.
It just won't provide all the nice cryptography.
Exactly, yeah. And, sometimes that's good, sometimes that's not what you want. It's entirely up to you. Okay, next few slides talking about I/O, and this probably has already come up. Yes?
The answer that you made was clarified because we were
No. Would you like to? What do you mean? I don't know what you're saying.
Okay, so
This is Ken.
I'm Ken Grant, the development manager. And you may want to back the mic.
Yeah, give like a visual hand, like I don't know if it's on or not.
It should be. Can you hear me? Does this work? Good. It should be clarified that the way the thing is being technically built is not reliant upon a TPM. There are business decisions associated around what are the characteristics of when you have a hypervisor. What do you get? What does the user think he's getting when he's got it? And all kinds of other different associated expectations. Based on those expectations, there will be business decisions made as to whether or not we allow the hypervisor to install whether or not the TPM is present. So Paul's answer is actually correct, completely correct, but there's another side to there's another facet to this problem that I think I need to clarify.
Network, we're already used to, as application and OS developers, treating the outside world as adversarial when we are talking to the network. We normally think of the outside world as sort of starting, I don't know, at the first router or on your subnet, but the community has done a good job in layering protocols in the networking space so you can sort of wrap crypto around data you send outside and receive from others. And so this is something we can directly apply in our environment. We're just sort of extending the boundary of whom you trust from the wire coming out the back of the box to the virtual NIC, if you like, running within the box. But everything we know now can be applied. Disk security is, in some senses, very similar. In some senses, is different. So the similar thing is, the disk is owned by the primary. The primary is where you're going to be getting all of your malware. The guests will be storing data on virtual volumes managed by the primary, so they can be modified and people can peer inside them. So that's sort of the same as with the network. Things that are different are a couple of things. First of all, the disk is sort of a critical part of the infrastructure of the PC, and so most people most of the time are going to be booting the hypervisor off the disk. So if the primary is responsible for the security of the hypervisor image, then unless we do something, the hypervisor is going to be only as secure, if you like, as the primary, which is only as secure as the security configuration and the apps that run there. That's true of guests as well. Guests are going to be loaded off disks out of virtual disk drives. So even if the hypervisor doesn't get corrupted, guests can. So what can we do about this? We can throw the TPM encryptor at the problem. If you can store a key somewhere, and I've described how the TPM can help you with storing a key, then you can wrap crypto around data that you ask the primary to store for you, and you can do a crypto check on data you get back from the primary to see whether it's been tampered with. So you can do this at any level you want, data blob, file, disk, volume. You would like the EFS to do this for you. You already have an encrypted file system. It does wraps crypto around files that are stored to the hard disk. Unfortunately, it is inadequate for our purposes. It does confidentiality, but it doesn't do integrity checks. So what this practically means is sectors can be modified within an EFS file system or volume or subdirectory, and EFS won't detect this, and with high likelihood this could be used as an exploit on the guest. So you're not going to get data out of the guest, but you can change something in the EFS volume, you can reboot the guest, and the guest will misbehave and maybe tell you all the things you wanted to know anyway. So we have to either fix EFS or we have to provide another system service which provides the guarantees we want, which is integrity and confidentiality. And what we're probably going to do is put a layer on top of, what we're certainly going to do, is put a layer on top of the virtual disk servers provided by VPC, which adds the confidentiality and integrity guarantees that we desire. Yes? Fixing EFS will be pretty hard. It looks like it will be easier to do it at the volume level than at the EFS file level. I can't tell you right now that the performance that we're going to do is going to be, what the performance is going to be. It's probably going to be a 50% slowdown, whatever we do, because you've got to write your integrity data somewhere, right? And you have to provide the same transactional guarantees in the virtual disk that are anticipated by the storage stack. Otherwise, things are going to break. So it's not easy, It would be surely nice if we had a non-crypto storage service that was not which was not owned by the primary, but that's sort of the world we're in. We've got some prototypes running. We haven't done all the performance optimizations that we know about, and once we've done those, I imagine there'll be a few that we don't know about yet, which we'll have to be looking at. It's weird. Okay, input and output, next two slides. User input, if we're concerned about spyware or people, sending Windows messages or whatever you want in order to, say, change the security configuration of the hypervisor. If you're relying on the primary for this service, then you are probably not having interesting security beyond what can be offered by the primary today. The remediation we have is some changes to USB host controllers to conceptually, Ken will dislike my simplification here, but conceptually do the first step of assigning a device to a guest. I'll show you in a few minutes that we have a Windows-based OS configuration where we can put drivers that are out of the primary. Input is one of the things we're going to do there. We're still not quite at a fully independent device driver in the primary, because that's just too hard right now, but we're getting there. Stack? Which stack? Oh, okay. So right now, the HID stack, Ken wrote this, so he should be speaking, but the HID stack basically routes input from the hardware up to whatever window has focus, whatever's going on. So what VPC has done, or anyone who's built a hosted VM is to route the data not just to applications, if you like, but also to operating systems. So this is what I'm talking about. We have a piece of code that is demultiplexing input from the user to applications. That naively you would say, okay, we'll just represent a operating system by something like an invisible window, and if that operating system has focus, we arrange that this invisible window has focus. It gets all key input, gets pumped into the bottom of the input stack in the guest, and it does its own branching out to its applications. Output is probably the biggest nightmare I personally have. It's really, really hard. You would like to be in a place where the primary couldn't see every pixel you put on the screen, but video card drivers are exceedingly complex. We will eventually probably do better by moving the video card and the video card driver into another guest and letting it be part of the TCP and multiplexing input from other guests that want to use it. But we're sort of not there for V1. The conceptual solution we're adopting is to essentially, it's another instance of, we're not using crypto, but we're moving a device driver into a more controlled guest. And people don't want to have two video cards, so we have an overlay surface that's managed by another driver. We're carefully controlling the definition of that hardware so that we don't have to support an open driver model within the TCB. Big compromise. Don't see it getting better until the graphics guys stop putting in new stuff at such an amazing rate.
Where is the second video as part of Longhorn?
It's a guest running in a stripped down version of Longhorn, which essentially is going to be NTOS kernel plus a couple of other drivers and HAL and support code. It has the internal name TSPWin. There's a slide on it in a minute.
And the original
the trusted surface, if you want to call it that, is an overlay on which the driver controlling the trusted surface can control the opacity of the pixels. It's a name for a video surface that sort of sits conceptually, Z order right on top. So essentially what it means is if the TCB, if we're talking about the TCB including this driver, wants to write a dialogue on the screen, they get to obscure anything else that's being managed by the primary and any other guests of the primary.
And the hardware supports overlay semantics generally?
Yes. And you can make it, you can change the opacity to move it behind. You can cut a corner out of it if you want it to be overlapping windows. If you want to do something as simple as have UI to administer the hypervisor, then this is probably, and this is sort of level of thing we're thinking about. Sign this document, then simple text dialogue without any acceleration is perfectly adequate. If you have aspirations to do accelerated 3D without taking a security dependency on the primary, then you have a problem. We don't have those aspirations, so yes.
I have an application question on the wall sciences as well as my grasp of the technical science. But my understanding is that one of the goals, the security goals, at least from my remember a year or two ago, was to be able to assure a program that it could output things to the screen in ways that cannot be tampered with, and also could not be intercepted and copied.
Yes.
Now, I'm assuming that's still part of the goal, even though this is in the video stuff in the primary.
No, okay, so what I've actually described exactly is addressing and meets those promises and guarantees.
So it does meet it.
It does meet it, yes. Again?
To explain,
yes.
Well, unfortunately, not again, but rather
differently.
In a way that
Right. Conceptually, we have two video cards. We have a video card managed by the primary. We have a video card essentially managed by the hypervisor, part of the trusted computing base. The video card managed by the hypervisor or the trusted computing base is a very simple one. It will feel like a video card from 15 years ago, but it can put pixels on the screen. Conceptually, we mix them before they come out of the VGA at the back here, and whatever's put on the screen by the little simple video card always goes on top of what's put on the screen by the other video card.
Okay, now that actually needs to follow. One thing which some people think of as a great feature and other people think of as a horrible flaw is the possibility that the trusted computing base could be used to protect software, or this opportunity to protect video.
Media, yes.
Exactly, media from being intercepted,
yes.
hijacked, while it's decrypted and forwarded.
Yep. So this feature absolutely enables that use model. I don't think I want to get into the challenges of building a DRM system based on these technologies. One thing I will say is the thing's going to be so slow that you don't have the motion DCT, blah blah blah, all the things that normally you expect the back end processing you expect on a video chain to give you good quality video is not going to be present.
So when you say enables,
yep.
you mean enables in kind of a way that allows people to put up text, let's say, but doesn't really enable use of a computer as a secure platform for playing movies. Or no?
It's not going to be HD or DVD quality full screen. It's going to be 640 by 480.
Oh, yeah.
But
Still nothing preventing me from, say, having a DRM in long form that leverages all the other mechanisms to prevent somebody from accessing. It's just long form is probably going to be easier to hack.
sure. Yeah, sure.
Oh, so there are going to be kind of security assurances in the primary. It's just you can't be. That in theory we should be confident about.
Yeah.
But in practice there may be just more loss.
So there will be, but that's not represented by this group. I mean, there's a whole team of people who go down to Los Angeles every other week and beg with the content guys to license content to the machine. They will not be in V1, possibly V2, possibly V ever, making use of these technologies, because they're doing a careful balancing between quality and security, and basically they just want the bits. They don't want it to be secure, right? They just.
But Hollywood does want it to be secure.
Yes.
So if I can just ask one more question, I'll stop on this. But so they can run in Longhorn kind of a high quality video, but then I think Hollywood will be worried that somebody else, that there's a process running in the background capturing all those bits.
Yes.
Through the high performance Longhorn video card access and not through the secure but low performance.
Yeah, and they should be worried. And they should be worried. It's going to be.
So this basically does not yet enable until things get a lot faster and more effective.
Correct.
Secure,
Correct. And if I were to try and enable such a thing, well, let me not even answer that question. That's.
It must be more of the story, right? It must be one of the usual things that would happen, a special kind of color to the window or something like that. So
Yes.
you know it's a hypervisor window and not spool.
Yes.
So what's your current thinking on that?
The current thinking is you share a secret with the trusted computing base, and Windows are decorated with that secret. It could be that desktops are decorated with the secret. There's a secret desktop, and you switch to the configuration desktop, and it's clear. It's not great, but it's not going to get better until you trust the boot process of the machine more than we can now.
Quick another question on graphics cards.
Yes.
Presumably you're making use of facilities provided by the graphics card to do this.
Yes.
So you now need to trust the graphics card.
Yep.
So what if I buy a dodgy graphics card that looks like a good one, or reprogram the graphics card?
Yep. You'll be reading a cert advisory about it. That's all I can tell you. It's sort of we're trusting the CPU too. We're trusting memory. We are not doing any use models where the owner or administrator of the machine is considered adversarial. If you read a cert advisory which says you've got a dodgy piece of hardware, you can say, okay, I'm prepared to take that risk. Or
But isn't it very likely that the simple video card would be integrated into the chipset? And it's not like it's a replaceable component the way the 3D card.
So one of the reasons that the 2D surface is simple is because we think the hardware guys can get it right. I don't think there's much in the way of a middle ground between simple video card and open driver model third-party video card. Probably there is a middle ground in Microsoft written video card, although even that's hard because the sort of model right now is up in user mode, you prepare this whole big list of instructions you want the video card to do, and you pass it down to the video card without really much intervening stuff, and that's done for performance, and the security implications are just horrible. You can ask the video card to blip from user mode. Okay, that's the end of the talk about the hypervisor trusted computing base. The remainder of the talk is the sort of guest security remediation and. Okay. So here's a picture with rather more acronyms than I would like on it, but it is illustrative. So, a bunch of virtual machines running different operating systems. For a pointer. I will be talking about. We've already talked a lot about the primary. It's the guy that owns most of the hardware. I will be talking primarily about the other guests here, what they are, how we're building them, how we're configuring them. Here we have two things we're conceptually calling red and green. It's basically a full OS with different security configurations for different purposes. And we have two other OS instances that are conceptually part of the trusted computing base. One of them is going to run a few drivers and system services like a reference monitor for the whole platform. One's going to provide administration. Maybe it'll end up as just one. Maybe it'll be two and we're done. I don't know. And the other one on the right-hand side is a high assurance development environment for third-party applications to run. So the next three slides, I think, just go into a little bit more detail about what these building blocks are. Already talked about the hypervisor, already talked about the primary a lot. The other ones are building off NTOS kernel off Windows and various build targets that we are getting, working on getting built out of the NT build process. This is leveraging an effort called componentization, where we're trying to reduce the interconnectedness of Windows so that you can sort of say, I want a bit of this and a bit of this and a bit of this and plug it together, rather than everything turning into, basically once you leave NTOS kernel, everything turning into an interconnected mass, so you can never really leave out anything. People are doing this at some level everywhere within the company. At a serious level, it's being driven from base up. So my guess is that in the Longhorn time frame, there will be relatively good componentization. Low down in the system, and still everything up in user mode is going to be very, very interconnected. And that's a challenge. So one build target we're calling TSP win, Trusted Service Provider win. It's basically start with the kernel and work out. So it's going to be NTOS kernel, the HAL, a few device drivers. Will form part of the Trusted Computing Base for high assurance guests. It will provide system services to the rest of the guests, like a reference monitor. It's going to be part of the TCB and will be authenticated by the hypervisor. So it's not going to, the hypervisor is not going to let you run a bad one. And it's, in my mind at least, sort of the building block for this vision when we move towards device drivers all over the place and DMA remapping and everything. This will sort of be the building block for this future vision of the OS. About 1 million lines of code, probably. Next few things is we're adding essentially the ability to run interesting user mode applications with the UI. And because componentization is in such poor shape right now, we're probably going from 1 million lines of code up to 10 million lines of code just by getting, create window or something like that. So this should be conceptually thought of, rather than talking about NT kernel and working out, this is start from Longhorn and pull stuff out until it's too hard to pull anything more out. And so Longhorn remote services removed. This admin win thing, it's for administration, network administration, and local administration. It'll be talking to the secure I/O to provide some meaningful security beyond that of the primary for administering the hypervisor. SecWin is going to be very close to admin win, but is the third-party programming environment. We are leaning towards a model where we just expose a third-party programming environment for managed programs, because the API exposure, the fact that Windows is quite easy to exploit, is going to be easier to do there. I have a few more words about that later too. Okay, next two things are sort of more the mass market general purpose OS that users interact with. And the sort of mental model we have, which I think is only approximately going to translate into what actually gets built, is we've kind of got the ability to have more than one version of the OS running with different security settings, and we have these conceptual models that we're labeling green and red. And red is the one that you can use to surf the internet with, and it's it's configured to let you get your job done, but you're going to be discouraged from doing anything that requires security in that environment. Green is the one that's going to be much more tightly configured, and you're going to be doing stuff that your corporation wants you to do, or your banking or something like that. So the value proposition, and this is a value proposition that sort of seems right to a bunch of engineers but hasn't really been fully tested with our customers, is that we do know that locking windows down tightly right now provides usability challenges for our customers. So they tend not to lock things down as tightly as they might want to, because then it gets in the way of what people can do. So the presumption is that if we can provide 2 or 3 or more environments which can have different security configurations, then an IT department can build and administer a VM that has limits what you can do, and that's where you're going to interact with your corporate services and corporate data. And you'll have a red machine, which is protected from the green machine, where you can surf the web and buy stuff at lunchtime and whatever else you do. Let's get back to that. Yes. So usability is key. That's the sort of thing here. And is this, this is sort of like a conceptual model, and I'll get back to it in a little minute, but should it be 2 machines? Should it appear to be 1 machine? Should I administer it? How should I interact with it? I don't think I'm even going to bother with this slide. Okay, so a year ago, we were building a high assurance guest, which wasn't going to do very much, but we had pretty high hopes for its exploit and bug rate. It was probably going to be a few tens of thousands of lines of code, and we were building it in a sort of high assurance development environment, which Tim's going to be talking about. Now we've kind of swallowed this 10 million lines of code, which is it's battle hardened, it does a lot, but we shouldn't just think we can drop it down in and provide the similar security guarantees that we were going public with a year ago. So what can we do to help here? Sort of 3 things probably. Internal guest protections, configuring the OS itself for security, leaving stuff out of the OS, and stuff that the hypervisor can provide for you, which is limiting what can get in and limit what can get out. And I have a couple of slides on each of those things. So leaving stuff out of Windows, this is essentially building off componentization. We're driving probably more aggressively than anyone else in the company to make this happen. But as I said, it's difficult because everyone has other priorities for Longhorn, and everyone's very busy, and this is sort of difficult.
Is that a technical difficulty?
I imagine there are.
It's an inertia problem.
It is an inertia problem, but sometimes I think it is technically difficult. I mean, if you just 2 million lines of code modules that are sort of, you have to implement it yourself or you can use this other guy. You have to implement it yourself or you can use these other guy. And if you want to split those 2 things up, then it's a lot of work.
Does it need a lot of duplication?
I would like to think that we have taken use by this, take a bit out of here, drop it down 1. Don't know.
I have to say that when we first started hearing about Palladium, before we got involved in the technical problems of what kind of a hypervisor is working,
Yep.
everybody was all upset about the fact that you were asserting that the code that ran through each partition was going to be small and well-defined, and we all said, yes, but the Windows people, the Office people are going to say, we want to run Office applications. Next thing you know, it's for people to add more and more stuff to that, and the result is it's not taking something.
And you were spot on.
Well, we were wrong, because we thought it would happen after you released the product.
Okay.
But now it's happening long before it's released.
Yeah, and it's been a source of profound pain to me getting this balance right. So I'm hearing you, and I've lived through it.
So is it still worth doing?
Do what?
Now that we've got all these funky partitions,
Yeah.
is there going to be enough benefit to be worth all of the development investment?
So this is is it worth building a hypervisor rather than fixing Windows problem?
That's one version of the problem.
That would be,
There's another version of the problem. Is it worth supporting so many things is it worth having three versions of Windows instead of one? That is, let Longhorn be, hope it evolves better, and don't ever build attempt to relocate one because of or a partition.
Didn't understand what you said.
forget trying to have different reds and greens and purple Longhorns.
Yep.
Just have one big, buggy Longhorn and live with it.
You can have as many Longhorns as you want. I want them all to be 100 million lines
Yeah,
long,
yeah, yeah.
rather than having any 10 million lines
Yeah.
long. Figuring that if I run Word in one,
Yep.
then when it goes south, it won't trash my spreadsheet.
Yeah, I think the big value benefit is in the scenarios you're talking about, red and green.
And there was a study done with the min-win base environment, which is actually bigger than what we're doing right now.
I was just saying there's actually a study that was done based on the min-win environment, which showed that going back and looking at the QFEs and defects that were shipped in Win2K versus the min-win version of Win2K, that it was a pretty high percentage of off-the-top cruft that when that stuff wasn't in the system, that was the highest percentage of the vulnerabilities and bugs that had gone into QFE. Doesn't mean there aren't going to be any because you still have a sizable amount of code left, but by taking off what might be a disproportionate percentage of bugs for the amount of code that was removed, I think we actually did see a good amount of benefit in that. And so, yes. These were, but the issue was knowing there are going to be bugs in a system, by paring it down, the min-win environment wouldn't have been vulnerable to, even to start with, to these issues. They wouldn't have had to have gotten fixed in that SKU.
Right, but the other way to look at it is in your gold machine, run, in your untrusted machine, run the current version of Longhorn, and in your green machine, run Longhorn version -3. Because if the top bugs are the ones you're fixing anyway, then if you use use +3, -3. That is, you have use an old version in the trusted machine and a new version in the trusted machine.
So I think surface area of the attack surface is something that we're trying to minimize here. So by actually removing components that may have bugs that haven't been found yet, still, even in that N+3 SP3 version, if those components just aren't in the system, you can't have a vulnerability in them.
Okay, let's move along. I'm hearing what you're saying. I am sympathetic to what you're saying. Okay, so this is addressing this is relevant whatever the OS instance. The OS has got much better over the last 3 years and markedly better with 5 years XP and XPSP2 Springboard in protecting itself. And so these are the sorts of things we're seeing in the Longhorn time frame that are going to be relevant security knobs that can be turned by an OS administrator to reduce the fraction of bugs, if you like, that you read on cert advisories that are actually result in exploits on your system. So OS integrity, it used to be the case we had this thing, system file protection. It was mostly about manageability and total cost of ownership. It wasn't really about security. Now the loader team and the process kernel startup team, if you like, are doing a little bit more authentication than file name when you load, when the loader loads the driver, the kernel, and the kernel loads its HAL and stuff like that. So that sort of variants of secure boot are being implemented early on. Further up, the boot process drivers are being checked more stringently for if they're good before they get loaded into the kernel address space. Network protection, these seem to me to be the top three things. You have personal firewall. You can configure IPsec to just sort of say, I don't want to talk to people who can't authenticate themselves properly. You can sort of mandate on a corp net that you always go out through a VPN, so you're letting some other guy, presumably running a firewall, offer protection on your behalf. Windows is big, and you have to think about threat models, but with 60 million lines of code, it seems to me that you're just going to be having a bug a month forever. So one thing you can do to mitigate that is to say, bugs can only be exploited if you can call the function, the system call that allows you to get at the internal data structures that allow the bug to happen. So one of the things in XP is administrative restrictions on what programs can load. So this vastly reduces the attack surface if you're prepared to configure a machine with this sort of lockdown policy. Configure a machine so it can only be remotely administered. There's this behavior blocking thing called Mako, virus checkers, plenty of other stuff. Of course, if you're running in a VM, you don't need third-party drivers, so that's a whole body of pain that you don't need to suffer as well. And we're looking at tools, security configuration, skeletons, whatever, to allow this to be easy to manage. What can you do? What can the hypervisor do for you? It sort of can a hypervisor administrator can. Well, the hypervisor also has to provide some, peer authentication. If you want to talk to some other guy to get some service from him, it's a good idea if the TCB provides a service that you can authenticate him as being a good guy. And for V1, there's also going to be a discretionary access control model where if you make an IPC mechanism and you just want you and your buddy to talk to it, then you can access protect it. So that's honored. Beyond that. The interesting thing to think about is various sorts of mandatory access control. So what can the hypervisor TCB do for you in terms of helping you secure yourself, or having an administrator which is separate from the OS administrator, sort of firewall the client OS so that it can't do certain things. So in one form or another, this is sort of mandatory access control. And I guess another question I would have for the room is, what do you think? I mean, how it quickly becomes difficult when you do this. If you think about sort of the important things you want to do in a security configured environment, is you want to do email. That's sort of one of the archetypal examples. And how high up the network stack does a Mac firewall have to go to provide meaningful security against a bad attachment or spam or whatever? Anyone have any thoughts? I mean, it's certainly, we're looking at it. We have planned to do it. It's just Mac systems, when in the old days when it was just you can see this bit of the disk, or were conceptually much easier without the rich connectivity and protocols and tunneling protocols that we have today. And
is there some possible story where you don't actually do that, but if you want to do Mac sorts of things, you do it on top of the CLR?
Yes, we haven't thought about that. It is certainly the case. It depends on what you think your trusted computing base to be. So for that to be meaningful, you have to believe that the CLR provides the type safety and separation guarantees that the CLR purports to do. The CLR is millions of lines of code. So you have to take that leap of faith, but Mac systems, the way I look at it, and this is sort of certainly a naive opinion, is that interesting Mac policies require you to do more sophisticated things than just say, I'm prepared to connect to this network, I can see this disk sector, I can read this document. It's more, everything interesting comes over one pipe. How high up the stack do you have to go inspecting things in order to make these sorts of security determinations? Firewalls do this, right? So it's not a problem. It's not a problem that other people haven't looked at. But given limited engineering resources, is it better teaching Outlook, say, to disambiguate mail from good guys and bad guys, and shooting one off to Greenwin and shooting one off to Redwin, versus teaching the firewall to understand SMTP or whatever Exchange uses, and doing that on behalf of the OS? What does it do for you if you do Mac? One thing it does for you is it allows you to have a separate hypervisor administrator than guest administrator. This is obviously a good thing. The other thing it does for you is, if you think about exploits and bugs, a firewall is not going to be outside your process space, is not going to be markedly different than the same policies implemented inside your address space for people trying to get in. It's going to be the same code. The interesting thing is, once you're exploited, what can you do? If you just have a discretionary access control system and someone breaks into you, then there's no one stopping you sending, code red packets all over the world and bringing down anyone else who's stupid enough to be listening to you. With a mandatory access control system, once your OS is exploited, you are still constrained in what you can do. So if you're worried about spyware getting onto a corpnet and then emailing out the contents of my documents to some news group somewhere, then that is something which is a restriction that's easier to enforce. Not easier to enforce. It is possible to enforce that outside the guest with a Mac system, and not possible to enforce it inside the guest with a DAC system, because the presumption is that you're exploited.
I'm confused. It seems like there are two things on the table. One is to do some kind of filtering.
These aren't on the table. This is really, I put this slide up to get input, because this isn't on the table for the next years.
So there are two ideas that are being discussed, and I don't think they're being separated, and I want to understand why you're not separated. One is the idea of filtering at the perimeter, or a firewall or a hypervisor firewall, and the other is to do something like MAC, which is not about filtering, it's about blocking behavior. And I see them as orthogonal, and in particular, I see the real issue is going about trust. And the things that you trust, you're prepared to impose less stringent policies on, and the things you don't trust. And exporting intelligence to the perimeter about the application is a bad idea because it duplicates things in the system.
Yes.
And so what you want to do is have a demultiplexer, which demultiplexes based on trust.
Yes.
And you want the stuff that goes into a world where it was untrusted, you want to impose more draconian behavior restrictions.
Yes.
Mac may be the way to do it.
Yes. So Mac I was just using as I was not being sufficiently precise, and I wanted to redo this slide, but I didn't get time this morning. I mean, when I'm saying Mac, I'm sort of saying there is a hypervisor administrator separate from the guest administrator who imposes policy, and one of the policies was one of the pieces of code, and one of the policies implemented by this piece of code that we've been describing is exactly what you just described, a multiplexer red-green that, maybe the TCB is the Exchange server and does that on your behalf. Maybe it's a piece of code running on the hypervisor and all mail messages are signed, or a source IP address or whatever.
All right, so let's look at that picture. I don't think that's a hypervisor administrator, because my picture is by a guest. And that guest demuxes the real wire to the ISP.
Yep.
And the administrator of that guest is the one that's going to impose a policy about where stuff that it demuxes goes. It's not the hypervisor, because the hypervisor doesn't know about demuxing communication.
Okay, so that we're probably arguing about what the hypervisor is. I'm sort of extending it out to be the trusted computing base used by guest and administered by the hypervisor administrator. But if it's the primary, then it's the primary. If it's another piece of code that's running in another partition, then it's that. I probably just should wrap up here. I'll leave this up. This is essentially my last slide. So this is sort of saying that, you know, red and green are convenient mental models for this world where we have two OSs configured differently. We have aspirations to go beyond that, which is to say that in many regards, entirely from the perspective of most users, and in many regards from the perspective of a corporate IT administrator, it's kind of just one box. And the hypervisor trusted computing base sort of does the right thing with data, if you like. You know, you click on a bad attachment, it just makes sure that, you know, nothing bad can happen with it. The user experience is a bunch of windows composited onto just one desktop. It's going to take a few steps to get there, I think. It's easy to get there, and there are real challenges here trading off usability and security and tensions here. So multi-year effort. I don't think we have good answers at this point.
Is there a white paper for this talk?
For this talk?
Or for the red-green mini-win vision of the world?
There's no white paper out there that I am happy with. So I'm not going to offer anything at this point. It is being worked on by some very capable people at this point. So I see things getting better.
I guess because it would be useful to have something that I could look at and think carefully about
Yes.
justifications, and obviously sooner ignore
Yes.
development is better than later.
Yeah. I feel like this is something where we need help and input, and would be delighted to have that have that conversation with you.
We'll probably have some discussions about how to set up feedback loops anyway. You know, so once we get that sort of mechanically figured out,
Yeah.
we'll bring it back into the discussion.
Sure. I'm basically done.
Okay.
Yeah, that's what we've been doing. It's hard.
Great, thank you.
Okay, thank you.
Well, right now we got 15.